So you have this table on your sheet. If you so anytime I need to get extra stuff, or I look at it and I'm like, I don't think this has everything it needs, definitely check out that sheet and check out that part of the table, or that top part of your sheet, and it may have that extra information that you need. So let's go ahead and get started. And I try to work these out ahead of time, but like I said, I've been sick and math is not my strong suit. So if something is a little off, or the math is off, just please send me an email and I'll look over it and see, because like I said, I'm going to try my best to not screw up any math, but math is not my strong suit, especially when I'm sick. So, okay, so this one asks how many kilowatt of energy could be generated by a coal burning power plant that burned 250 tons of coal and was 40% efficient. So there's two ways you can approach this problem. You can do the 250 tons and you can take 40% of that, or you can just take the 40% off at the end. I prefer to take the 40% off at the end. Okay, let's try this again. I'm trying to put my hand on the screen and it's not liking it. Okay. 150 tons. Okay. So what I'm going to do is I'm going to convert these tons to BTUs, and that's a conversion I got from that table on the first page, on the first slide. And 2.5 times 10 to the 7. Okay. And then I'm going to convert these BTUs to kilowatt hours, because that's what it's asking for. And again, this conversion is on the table on the front slide and at the top of your paper. Okay, so this gives me 1.83 times 10 to the 6 kilowatt hours. And now I'm going to take my 40%. Okay, so I'm going to multiply that by 0.4. And that's going to give me 7.32 times 10 to the 5 kilowatt hours. I'm not going to count sig figs and all that stuff. If you want to write the whole thing out instead of scientific notation, that's fine. But that's your answer for problem 1. Problem 2, I have several students that have turned this one in and gotten it incorrect, and here's why. So this is 5.2 times 10 to the 4. And a lot of students are just writing 5.2. And so they're getting the wrong answer because they're leaving part of that number off. I'm going to convert the watt hours to BTUs. And again, this conversion is from that table. And then I'm going to convert the U's to cubic feet. So basically, when I start these problems, I just kind of, I start with whatever they give me, and then I just kind of like convert until I get what I need, if that makes sense. So then I get 1.83 0.72 times 10 to the 5 feet cubed. And this is like the last one where you could have done the 65 at the beginning if you wanted. And then I'm basically going to multiply this by 0.65. And I'm going to get 2.65 times 10 to the 5. So a lot of students are getting 26.5, and that's because they're not doing that 5.2 times 10 to the 4. So make sure you remember that 10 to the 4. That's important. So now let's go to number 3. I'm not going to lie. These type of problems are probably like my least favorite. I really don't like specific heat problems as a rule. So let's get started, I guess. So we have 30 cubic feet, so we'll start with that. And we need to change the pound of water. So if you look at your table, you'll have to convert this to BTUs, and it's really the only conversion that has feet cubed in it. So that's another way that you know that that's the conversion you need to use. And then now I'm going to multiply this by 0.9 for my 90% efficient. Okay, and you can multiply by 0.9 at the beginning or the end. I just chose to do it at the beginning, but you don't have. I chose to do it, I guess, in the middle, because I'm just kind of showing you different ways to do it. The important part is that you take that 90% into consideration. Okay, so now we have this, and now we need to do like our specific heat. So basically, 1 BTU is equal to 1 pound of water per degrees Fahrenheit. Like that's like the definition of BTU. Okay, and we're changing it 20 degrees. Okay, so I'm going to cross these two F's out. I'm going to cross these BTUs out, and then I'm going to end up with pounds. And so then my answer is going to be 5.57 times 10 to the 5 pound H2. Okay. We made it through that one. Okay, now part 4 has a couple different ones, and your FRQs are probably not going to be this difficult because you're not allowed a calculator on the exam this year. So basically what we're going to do is the R value is 6.7 for a blanket that covers 25 square feet. This is how many BTUs will it save for every hour it prevents 1 degree Fahrenheit of temperature change. So we have a formula on your sheet. I've gone ahead and converted it, rearranged the formula. Okay, And this is basically the formula for R value, and then I'm just, um, just rearrange the formula. Now, a cool thing on the FRQs is, let's say you got this part wrong, but you got the like part B right, even though part B relies on your answer for part A. If you do the math for part B correctly, you'll still get the points. They still give you the points. So what I like to tell students, if you don't know how to do part A, just make up an answer for part A, and you pick an easy number, and then and then use that answer for part B, and that way it'll, um, since you're not going to get points for part A anyway, it'll at least save you some effort on part B. Okay, this should actually be 167.5. Okay, and I'm just going to convert this to cubic feet. BTU. So that's one of my BTUs. And this was 1 hour, they said. So if we want to do for a year, we're going to need to do 24 hours, and that's 1 day and 365 days, 1 year. Okay, so that's how much you'll save in a year. Now, let's do 5. 5 is about efficiency. So the first thing we need to do is we need to figure out how many BTUs is this. Okay, so we have 5,000 pounds of water, and then 1 pound is 1 BTU, and then we need to do the 25 degrees Fahrenheit. This is that definition of BTU, remember? Okay. And now we need to figure out what this 210 feet is. Okay. And then whichever one's the largest is going to be on the bottom, because you can't have a machine that is more than 100% efficient. So you can just put the one that is larger on the bottom. Okay. Okay, so this one was the larger one. So now we're going to do 125,000 over 2.7 thousand. And that's going to give us 0.576. And we just multiply this by 100. It'll give us 57.6%. So this one had 3 steps. Now, number 6. So in this one, we have 7 tons of coal burning, and we're generating 3.6 times 10 to the 4 kilowatts of electricity. So what is the efficiency of the generator? Okay, so this is showing us how many kilowatts. So basically, we're going to take this 7 tons, and we're going to put this in kilowatts. So we have 1 ton is 2.5 times 10 to the 7 BTUs. And then 3413 BTUs is 1 kilowatt hour. Okay, so it's going to give us 5.1 times 10 to the 4 kilowatt hours. And then we can take that and we can put the 3.6 on top of the 5.1. Remember, you're always going to put the bigger number on the bottom because you can't have a machine that's more than 100% efficient. Okay, so this is going to give us 0.705. We'll try that by 100, which is 70.5%. Okay. Now, problem 7 has like a million parts. I don't know if you guys have started on these yet. So let's see what it wants here. It says, if you replace a 75-watt incandescent light bulb with a fluorescent light bulb, it gives you the same amount of light by drawing only 20 watts. And then you use it for 4 hours a day. So basically, we're going to compare the two. Okay, so we've got 75 watts. We need to convert this to kilowatt hours because the answer, it wants our answer in kilowatt hours. So we have 1,000 watts in 1 kilowatt hour. And then, well, kilowatts. We'll get the hour in a second. And then we multiply it by 4 hours. There's our hour. And we end up with 0.3 kilowatt hours. Okay. Now, we can do 20 watts. Same thing. Okay. And now we can just take the difference between the two. So we'll do 0.3 minus 0.08. And we're going to save 0.22 kilowatt hours a day. The next question says, how much would you save in a year? Again, now if you had this answer wrong in part A, or you didn't know how to do part A, you could make up an answer for part A, and then if you did know how to do this one, you could put your answer from part A in here, and you could still get full credit for part B. So that's kind of like a little trick for the FRQs. So we're just going to multiply this by 365. I can write 365. Okay, so I'm going to get 80. Kilowatt hours per year. Okay, let's go to part C. The cost of a kilowatt hour is 10 cents. So how much money does the fluorescent light bulb save in a year? So we're going to take that 80.3 kilowatt hours per year, and we're going to multiply that by 10 cents. And we're going to get $8.03 a year, which is, it's nothing to sneeze about. If you have, 50 light bulbs in your house and you convert, that would be 50 times 8, which is, pretty significant savings. Now we have part D. Now for part D, it says it has this little fraction here. I believe they meant a decimal. So just put a decimal there. And so the first thing you need to do is you need to figure out your power. So we have power is equal to current times voltage. So if our current is 0.06 and our voltage is 0.75, our power is going to be 0.045 W. Okay. You may have solved that one before, a similar one like that. Use that formula in physics. Now it says if the solar cell has an area of 20 centimeters squared and collected sunlight when the solar constant was 0.8 watts per centimeter squared, what is the efficiency? Okay, so we need to take that 0.8 watts, 0.08 watts, and multiply that by 20 centimeters squared. Okay. And then now we want the efficiency, so we're going to take that answer we got in like 7D, like that just previous part. So we're going to have 0.0045, and I know that one goes on the top because it's the smaller number, and the smaller number always goes on the top when we're doing efficiency. And so I'm going to get 0.02, and we'll multiply that by 100, and it's going to be 2.8%. And that's a pretty small efficiency, but again, we're talking about capturing, light from the sun. So it's going to be very difficult to be very efficient capturing light from the sun. Okay, so how many solar cells would it take to run a 60-watt bulb? Okay, so our solar cell was 0.045 watts, and a 60-watt light bulb is 60 watts. So we're going to do 60 watts divided by 0.045 watts It's going to be 1334 solar cells. Okay. Now, part E. Okay. If the efficiency of a coal-burning power plant is 65% and the efficiency of energy transmission is 95% and the efficiency of the electric stove is 85%, how many BTUs of heat would be produced after 50 tons of coal have been burned? Okay. So basically we're going to have to calculate the efficiency 3 times after we've converted this 0.5 to BTUs. At least I'm going to convert it to BTUs first. You could, I'm just going to erase this in and start over. You could do your efficiency first, take all those percentages first, but I don't know, I like doing it at the end. I got this conversion again from that very first chart that's at the top of the problems page. So if it was 100% efficient, this is how many BTUs you'd have. Okay, but it's not. Okay. The first thing is the power plant is going to take some of that efficiency, and it's only 65% efficient. So we're going to do, we have to multiply this by 0.65. Okay. Okay. Now, we're going to lose some energy in that transmission from the energy to your house. Okay. And that is 95%. So that's pretty good. Okay, so that's going to give us 7.72 times 10 to the 6th. Now, the last place we're going to lose efficiency is the stove. Okay, so the stove is 85% efficient. So let's figure that out. Okay, so this will be our answer. Okay. This I believe. Oh, there's one more step. Okay. I'm going to leave this one. Well, I guess I could do it. I did all the others, so I might as well do this one for you as well. So the first thing we're going to need to do is basically turn these gallons into pounds. And that conversion, again, is on your sheet. And if these problems seem hard, don't despair. The problems on your FRQs are usually much easier. So if you guys, you've been doing the math on some FRQs now, you can see that those are a little bit easier. So hopefully these problems don't freak you out. So here we go. 1 foot cubed, 10, 31 BTU. 1 BTU is 1 degrees Fahrenheit, 1 pound, 15 degrees Fahrenheit, 6. So I'm just like, looking at the conversions I have and figuring out what I need to do to get, where I need to be. And I know that I want cubic feet as my answer, so I need to have that at the top, right? So we have 2.33 times 10 to the 4 feet cubed. Now that would be the answer if it was 100% efficient, but it's not. So, and this number was just 75 minus 60. See. That's how I got that number. So now I need to take this 2.33, I need to multiply it by 0.8, and that's going to give me 1.86 times 10 to the 4 feet cubed. Hopefully these problems were helpful to you. Again, I worked them all out for you, one, because I think they're kind of difficult, and two, because I kind of wanted to throw you a bone if you watched the recording or came to the live session. So hopefully this was helpful, and it will save you some time. I'll still be here for the rest of the hour, but